I'm just calling it Site 1. We had basically stiff clay that was overlain by peat and marl. I think about 30 feet, 35 feet of peat and marl that had very low blow count. I believe that was the N60 blow count as well. So we basically have a very, very soft layer. I would almost call it muck, the level of softness of this material. And you can see the yellow area is basically where a former kettle lake has over time basically reduced in size from the red dashed line, which is actually where the lake will flood into if there's heavy rainfall. And that's the basically Kettle Hole Lake. Those are formed, I think, by big blocks of ice melting as a glacier retreats in an outwash. So I'm sure everyone here can quickly ascertain that this is a project in the Midwest, and it is. And as I mentioned before, the lake has since retreated, and the present groundwater table is very shallow, around 2 feet depth. And essentially, these two roads are going to be reconstructed further, basically directly on top of that very soft area. So there is a need to improve the load-bearing response of the site soils to support the embankment surcharge loads. And the DOT for this project allowed for the rigid inclusion type used to be performance-based, and they actually let different bidders propose different solutions. And the only real performance criteria that I know of is a 75 kip axial resistance with 2 or few inches of settlement. Next slide, please. Okay, so as I said before, that southbound embankment had to be moved into the yellow area that had the softer soils. And there was basically the ground improvement technique selected was the use of helical piles, 4.5 inch diameter with a 20-inch blade near the bottom. And those went down, I guess, approximately 45 feet into the stiffer, more competent material. The target torque was around 13,000 foot-pounds. And you can see these kind of installed in an array of about 175 of these rigid inclusions. Each of them also has a 2-foot diameter load transfer plate on top of them to facilitate transfer of the embankment loads to the helical piles. I should also note here that the embankment fill was not just haphazardly dumped. It was there was a highly rigid LTP created load transfer platform that consisted of alternating layers of geogrid, 1 foot of compacted stone. I can't remember what size stone, but very rigid. And then every foot there was basically geogrid. So you have this 5-foot, basically almost rigid plate sitting on top of these very rigid helical pile elements. And the instrumentation that was used on the project were earth pressure cells and vibrating wire settlement systems. It seems to be running away. Anyway, there's 2 clusters of these, and you can see that on the left side, we have earth pressure cells on top of and in between the helical piles, and we also have settlement systems on top of and in between. So the idea is that we want to figure out, probably obvious to everyone in the room, we want to see the load distribution at the plane of the pile caps of the helical piles, and we also want to see the settlement distribution across those piles to verify performance. Next slide, please. This is a close-up just to show that we did do some cleanup, and we sort of filled the trenches, and we actually ran our hydraulic lines and cables all to the far side of this image with the reservoir box, which you'll see soon. All the devices we deployed were from Geocon. earth pressure cells, and basically model 4660 vibrating wire settlement systems. Go ahead and go to the next slide, please. This is the logging apparatus that we used. These are fairly simple to install, 4-inch by 4-inch timbers being dropped into basically a post hole dug hole, and then we just pour concrete. So it's actually really important to think this through because this measurement depends on the difference. It's basically, you have a reservoir level to the sensor, and it's a closed hydraulic system. So atmospheric pressure doesn't affect anything. The noise from this system really comes from thermal changes that affect the diameter of the hose, and that either pushes water up into the reservoir or pulls it down. And that's registered as a change in hydrostatic pressure, which can then be back calculated into either settlement or heave. So it's important that this system is mounted in such a way that the reservoir is fixed. Otherwise, the readings could really be unrepresentative of the true movements. And all of this is actually, go ahead and go to the next slide, please. This is what the guts of the reservoir look like. Each of those two hoses coming out of the bottom goes down into the ground through the trench to the sensor. And each of these reservoirs is full of 50-50 glycol water mix to prevent any issues with freezing in the hydraulic lines. The logging system, we used one of our various GeoCloud logging solutions. This one is a vibrating wire node with a wireless gateway combination. So we actually don't have to do any wiring with a screwdriver. We just have basically military quick disconnectors. So these are weatherproof. They work quite well. So that was the system on project site number 1. And I want to go ahead and look at some of the data. You can go to the next slide. This is what our typical project website looks like at Geo Instruments. Of course, the plan view changes, the sensor types and number of each sensor changes, but this is a pretty typical landing page. You can see that the trench that I showed you before is that brown line, and the logging devices that I showed you just now are the green dots near the end of the trench. So on the left side, we have our pressure cells, and on the right side are the settlement systems. You can go ahead and go to the next slide. And the data it came out so cleanly that I'm really happy to be talking to a lot of people that understand rigid inclusions and ground improvement. Just to go through a little bit of the details, about 12 feet of LTP and embankment fill were placed on top of these earth pressure cells and settlement systems. And each of those 2-foot diameter plates was basically supporting the contribution of a 5x5 area of soil based on the spacing of the load transfer plates. So if we just do a little back of the napkin math, I love 2-foot circles because, you know, we have the easy area. But if you look at this, there's a clear divergence between the two lines on the top, which are on top of the rigid inclusions, developing far more earth pressure, vertical earth pressure than the muck in between. So you can see that the load on the muck actually peaked before they were even 1/4 the way through filling. So the rigid inclusions were holding 100% of the load, if basically after only maybe 3 feet, 4 feet of fill were placed, maybe even a little less than that. And the data actually makes perfect sense when you compare it to kind of our unit weight, 25-foot square area, 12 feet of fill. That full weight would come out to around 33 kips. So if we just multiply our areas, basically area of the helical pile and the 11,000 PSF, and then the remaining 21.9 area of muck, and multiply that by the stress felt, we're very, very close, around 37 kips. So it makes physical sense. We're within a pretty close margin of what the theoretical surcharge should be, and the pressure distribution reflects that. And so the kind of big conclusion, unsurprisingly, is that the RIs are holding the vast majority of the LTP and embankment fill loads. You know, the muck is holding, it peaked around 600 PSF, and by the end of monitoring in November, it was down to 150 PSF. So the load on the muck gradually I should say load relief occurred from very early in the filling process. That's a function of how rigid the LTP is. All of that additional embankment load is going to the piers because it's basically sitting on a big steel plate that's sitting on rigid helical piles. So it's actually, these are perfect field conditions for measuring earth pressure with earth pressure cells, because there's no role of bedding and there's no role of soil disturbance, because we have a manufactured element with a compacted LTP on top of it. So there's no role for soil disturbance to affect readings. Am I running out of time already? Oh.
So Keller installed the helical pipes, correct?
Yes. 75 kips.
Okay. Did you do like finite element model for that? And if you did, is this close to the load that you predicted for helical pile?
There was not a finite element that I know of, but there were 2 top-down load tests, both to 75 kips. One settled 1.4, the other settled 1 inch. Yep. Obviously, those weren't instrumented though. We would have overranged ourselves. So we can go to the next slide, please. And, oh, okay. So I should have waited a moment, but I just wanted to kind of zoom the data out to show actually both of our, so these are 50 PSI earth pressure cells. So convert to PSF, it's about 7,300 PSF. However, the cells can go 50% over their range before they really, basically before the vibrating wire actually snaps. And so these delivered a stiffer load a stiffer load response than was actually expected by the engineers. And we overranged both sensors when they were about half a foot from topping off. So they were very close to the end of their filling when we overranged. But we got the data from the muck basically showing us that, hey, we don't have any more data from there, but we know that the load was gradually tapering off and that those helicals continued to hold more and more load as time went on, especially as more displacement developed, which we'll look at next. Next slide, please. So this is our settlement systems. Again, these are the ones that have the reservoir, the closed hydraulic line that goes to the settlement plate that's fixed onto a basically foot-by-foot steel plate. And although I recognize that this data is a little bit noisy, especially with we had some voltage spikes that caused those 3 blue kind of crazy looking areas, but you can see the reading stabilized eventually. And these 2 on the bottom were on top of the rigid inclusion, and the 2 top lines are in between. So I think we can safely qualitatively at least say that the helical piles displayed a very stiff response compared to the muck. I'm a little confused why I would have thought the purple line would be a little bit higher. But you know, the data doesn't always come out perfect. But we still got very, I think, clear evidence of less settlement on the helical piles compared to the muck, which makes sense. Next slide, please. Okay, so this leads us into site 2. And how am I doing for time? Am I, okay, great. Okay.
So this is your other case study. So on that first one, do you have any manual settlement plates to verify the fire system?
I tried.
So they all got hit?
No, they didn't want to pay for it. Settlement plates are on site 1. I would have liked some piezometers. I would have liked some piezometers to show load being picked up by the muck. they, budget constraints got in our way a little bit, but I think piezo's and an optical measurement or perhaps a shape array for the settlement profile would have been great for the data, but it would have blown up their budget. We did all this for less than $50,000 at site one. So it was that was a pretty hard number that we couldn't go beyond.
So ultimately, though, you used the settlement cell data to validate that. I mean, I guess the routing inclusion helical file system works, and B, the site for not going on. So I think the settlement file is flat.
Right. Yeah, and I mean, I should be clear that this stuff, the helical piles have a 20-foot blade at the bottom, and they were pinned into competent material that they got 13,000 foot-pounds of torque mobilized on their drilling rig. So that was their cutoff, and I think that's, I'm not a driller, guys. I don't know, but that was their target, and they reached it on both. And the load test on those particular piles verified the displacement was acceptable under the design load. And okay, that leads us into site two. So this project is a really good point of comparison because the surface soils are quite a bit stiffer than the first site. And secondly, a different rigid inclusion type, which is slightly less rigid, a stone column, were used. And the settlement and load distributions are, I would say, polar opposites of site number one. So I look forward to showing you this. Again, we used the same sensor types, especially if we only focus on the earth pressure cells and the settlement systems. But we also, in addition to those, we had vibrating wire piezometers and also some horizontal shape arrays. And this is kind of a just schematic showing each circle is an aggregate pier, 40-inch diameter. They went down about 45 feet. Top 20 feet is fairly stiff, and there's about 20 feet of weaker material and then stiffer material below that. You could go to the next slide, please. And this is kind of what the site looks like. These three, our first mobilization was for the piezometers, which are kind of on these PVC stick-ups. Those were interesting. After the presentation, if you want to ask me about the interesting installation method used for the piezos, I'd be happy to tell you more about it. But the basic idea is we installed the piezometers, and then we returned to the site visit, or returned to the site, dug trenches, and then placed our earth pressure cells and settlement systems on the aggregate piers. Go to the next slide, please. And so again, these are the exact same instruments, 50 PSI earth pressure cells. And I can't remember the exact range, but these are high range, high resolution piezometers for the settlement systems. You can go on to the next slide. And this is kind of what it looks like. So this one, that one, for example, is on top of a rigid inclusion. That one's in between, and those are both, I believe, in between. But it's the same idea that we're going on top of and in between the rigid inclusions. You can go to the next slide, please. This should ring a bell from our last, from our site number one. Obviously, we have more systems installed this time. 9 total. So instead of, each of these can house 2 instruments. So 5 boxes allowed us to house all 9. And we had all of this in a climate control connex, along with our other loggers, which I'll show you in a moment. So, okay, and all of our gateways are powered solar. So we don't really need necessarily power. It'll all run just on solar. You go to the next slide. And so after that phase was over, our customer then laid out a gravel pad, and it was after that point that we went to install the shape arrays. A little bit of reference on shape arrays. This is a device that Kyle knows a lot more about than I do, but basically you have meter or half meter long segments. They each have a triaxial MEMS sensor, which basically just tells you differential rotation along 3 axes. And it's basically a big L sine theta accumulated function from one segment to another. You can generate a settlement profile based on the angles and the known length of each segment. So in this case, we deployed 2. And because they placed the LTP, we had to bring out manual surveyors to basically, I don't know if you can see that little yellow flag there, but that's on top of one of the inner rigid inclusions. So we had them basically mark out 2 of those so we could, 2 points to make a line. That way we were sure that we were actually on top of a line of rigid inclusions. Go ahead to the next slide. And yeah, so we protected these in PVC conduit. I'll talk a little bit later about things to be careful about with conduit and SAAs. But you can see we just have SAA number 1 and SAA number 2 there. The point of fixity is on the far end. So those, if you're on an embankment, you want to be going at least probably 15 or 20 feet off of the footprint of the embankment, so that you have a point of fixity that you can then, you need a fixed point in order to measure a settlement, right? With the L sine theta function. Okay, we can go to the next slide. Okay, that's redundant. Sorry about that one. Okay, more PVC and spray paint. And I don't know, I put this one up because I try to go the extra mile. We could have just run a cable, but we dug a trench. This is kind of how we really try to do high quality field work. We dig trenches, we protect cable all the way until it goes into the basically Connex with PVC to ensure it isn't damaged. And then we cover that back, put gravel over it because they might have equipment roll over it and we don't want to break our sensors. So it's just kind of good housekeeping. And anyway, that's another photo of all of our sensor cables going into the Connex. This is what the logger box looks like for the shape array. It has a modem, other various power. It has a Campbell Scientific logger in it, various components. But that's pretty much how easy it is we have that coming in, a quick disconnect, and then the system is basically fully automated. Readings are being taken constantly, or every hour to 2. You can go to the next slide. So this is now the box with the bigger panel to power the SAA logger in addition to the 2 gateways for the other sensors. You can go to the next slide. All right, this is the fun part. So this curtain's kind of funny. I keep looking at that one corner. But anyway, I hope that this is clear, but earth pressure cell 1 and 4, which is the light green, so this line, and this earth pressure cell 4, the kind of lighter blue, is this line here. So those are on top of the helical piles. The other are on top of the clay. So the clay's holding all the load. And so this is a really interesting one because it shows the role of bedding. It shows the role of potential out of planeness of your earth pressure cell. Imagine that you have an earth pressure cell. It wants a full circular area, but if it gets on an angle, it's now not receiving that full pressure. It's getting the tangent, or it's getting the orthogonal force. So if that earth pressure cell gets out of plane, it may not give you the full pressure that you wanted to read. Also, if you install an earth pressure cell in less stiff material than the surrounding material, it's like a tunnel. The load will just arch right around it. So that's why I thought these couple of case studies were worth showing to a group like this, that the helical piles and the rigid LTP completely remove those factors that normally plague earth pressure cell measurements. A lot of the time, earth pressure cell data is highly confusing and they don't accept as much load as is expected. But in this case, we had one project where we got more load than expected into the helical due to the rigidity of the system. And then we have this second where the surface material, I think, was around a 15, 20 blow count. And these aggregate piers, there had to have been a soil disturbance or bedding issue because the aggregate piers are not receiving really they're getting about half the amount of pressure as the adjoining soil. So, you know, you can go to the next slide, by the way. Uncompacted gravel, just dumped. So that was another fact. That's a great point, that there was no LTP on site too, to facilitate that transfer of load. I believe there's ultimately there's going to be a lightweight slab going on it, a fairly lightweight slab, and I'm not exactly sure. That is a result of 12 feet of uncompacted fill on the entire area. Aggregate piers receiving little to no load, adjoining soil receiving the majority of the load.
Are you saying that this very stiff clay is stiffer than aggregate piers?
Yes, and the entire load is getting held by the crust. And that's why I opened this up. Let me know if I'm misinterpreting this, but I think it's interesting. I mean, what? I didn't say it. I didn't say that. It's a great job for us. It's purely for information and education. I just think it's interesting that these two things did the exact opposite.
So your original conclusion was just an aggregate pier,
Yes.
certain diameter, drill, backfill, and stone.
Yep.
That's good. As you put load on it, it's gonna settle.
Yeah, it's gonna bed.
Yeah.
That'll move down a little more, and then all the load will just go right around it.
But it pushes out itself where your helical pile is rigid.
Yeah.
Stone column is not rigid.
It's not quite, it's rigid inclusion, right? It's semi-rigid.
And it feels like it's compacted with, load transfer platform like a geogrid. You could have seen a different.
I think so.
Even if it was just like a couple feet, right? 12 feet, not even all of it.
I think that a load transfer platform would help if it was in intimate contact already with the aggregate piers, and if the aggregate piers were stiff enough under low load to engage the earth pressure cell. That's my gut feeling on that. I think the LTP would have helped. And you can go to the next slide. That was just pore pressure, by the way, and this one includes the previous slide. But I just wanted to show that we did pick up some excess pore pressure, and it wasn't always correlated with fill. Like this one, for example, was a big rainstorm. But most of them are kind of roughly correlated with where there was some fill. But these really big spikes are all rainstorms, just so you guys know. You can go to the next slide. And this is the SAA data, which I was kind of joking around that I just can't believe it moved so little differentially. But this is what the data is telling us, is that and these are the SAAs that we stretched across the RIs, going kind of alternating RI soil across. And both are showing less than 507 inches settlement. So to me, this would normally confuse the heck out of me, but in the context of seeing really high mobilized pressures on the clay instead of the aggregate piers, that whole load's just getting held rigidly on the crust, and the whole thing is not settling. That's what I believe is happening. But anyway, this definitely makes sense in the context of the load distribution that we saw. You can go to the next slide. And I zoomed this one out, but it's just kind of it's supposed to be showing very little movement from the vibrating wire settlement systems. And again, these are noisier sensors than a shape array by quite a margin. But you can see how they're all pretty much bunched, a little bit of heave, a little bit of settlement, but it's kind of all straddling that zero line. And I interpret that, along with the shape array data and the SAA showing no differential movement, that the crust is holding. Again, the crust is just holding the load and it's really not displacing all that much. Next slide. Okay, this is where I probably got ahead of myself throughout the presentation, but I'll just run through these again. And also this is where I really invite criticism and any comments where if I've misunderstood something, please let me know. I love learning. Okay, so rigid inclusion with load transfer platform is when that design is put forward, it's usually that the helical piles are supposed to hold the vast majority of the load. However, with an aggregate pier, at least this is my kind of understanding, is that they're actually meant to be more of a load sharing system where it's not entirely it's not super surprising that they settled the same amount because they kind of it's meant to stiffen the overall system and prevent kind of radial bulging. But according to a lot of conversations that I've had with different people, this is actually fairly typical for aggregate piers. And this was something I learned on this project, was that because I was telling my customer, hey, your inclusions aren't holding any weight. I'm a little worried. And then the response was essentially that is not unexpected and it happens quite a lot. And if that load somehow does break through the crust, then those aggregate piers will then become valuable. But I'm open to criticism and interpretation on this slide. That's all right.
The aggregate pier installation method, were the holes pre-drilled, or
Drill.
like they all got play.
They first dug an excavation that was dry. Oh, by the way, the groundwater table is very low on this job too. I didn't mention that, but they drilled and then they basically had this probe that delivered gravel and vibroed.
Was the intention of the design to stiffen clay with the aggregate pier installation?
Yeah.
Or was it just to provide stiff columns? Like if you didn't bring it post CPDs, think that you'd find that in between the columns the clay was stiffer.
Probably. Maybe. I mean, maybe. I don't know.
So maybe they did. Sorry.
I'm
I don't know what you're doing.
but anyhow, this came as a big surprise to me that it's not always expected that the rigid inclusion will take the load and settle less than the adjoining soil. It's apparently quite normal for them to settle the same amount, and they're sometimes designed to do so. So anyway, as much as I might have fumbled through this, it's my hope that comparing site 1 and site 2 are instructional, because in my mind, they show kind of these two different rigid inclusion types where we're trying to concentrate a lot of load into the rigid inclusion versus basically creating a load sharing system where the aggregate piers are working with the soil. And I honestly still have trouble with this concept because I think you have a rigid inclusion, it should hold the load. But this is apparently the way it is sometimes. If you go to the next slide, I think it's the last one. Oh no, I think there's 2 more. And here's some notes that I got ahead of myself before, but again, just big picture, if you're using earth pressure cells, you might get a stiffer load response than you expect. Size the range accordingly. We could have easily put a 100 PSI earth pressure cell on this project and had plenty of resolution. And we would have captured that last bit of earth pressure data. Also, out of plane issues with earth pressure cells on aggregate piers is a serious issue. So is soil disturbance in terms of measuring load concentration because of the stiffness difference. Whereas with helical piles, which are highly stiff even at low loads, with a rigid LTP, you're way more likely to get verifiable load concentration on your aggregate pier. I've always thought it'd be really cool to put a, I don't know if you guys have seen like the gun turrets that the military uses. They use this little thing called a slip ring. It allows electrical charge to go through a rotating device. I've always thought, why not put a little like a strain gauge in the inside of the helical pile near the tip, and then just have a slip ring at the top, and then you could measure not only what's the load up here, but what's the load down there. You could even avoid using earth pressure cells completely if you put a few gauges along the shaft of the helical. Never seen it before, but I hope I see it someday. And yeah, just the importance of the relative stiffness between it's not all about what's the stiffness of the base material that you're going to tip out into, but it's also important, what's the surface stiffness when we're evaluating, will the load actually get into the column or not? And I believe that's it, but go ahead and click one more. Oh, here's one more. A couple of notes on the 2 settlement systems used on site 2 is with a horizontal shape array, be careful about what size conduit you use, because if you use too large of a conduit, it won't bend and you'll measure very little deflection. I have like half a mind to think that affected the results here because it's so perfectly flat. But then I know it's an inch PVC and I'm putting, you know, I don't know, 1500 PSF on it. I feel like that would bend PVC. But that's one important thing. Also, make sure that one end is truly fixed on the SAA, or you have to somehow measure basically settlement of one of the ends to actually know, because if the whole thing moves down uniformly, the shape array won't tell you anything. With the vibrating wire settlement systems, two or three installations later, I've learned the hard way on the first job that we need to manage hydraulic line length, because what happens is temperature, even if this thing is buried a few feet underground, the temperature still changes. The hose flexes and it pushes the water up and down in the reservoir. If it's cold, the hose contracts, it pushes water up into the reservoir. That is registered as a settlement because there's more head on the sensor and it just thinks that the sensor moved down, i.e. settlement. So it's important. I wish I'd plotted it, but when you're looking at settlement data with these systems, you either need to plot it against temperature or you need to do a formal temperature correction, which is preferred. Another big thing is throughout the installation, prevent air bubbles from entering the line. I'm sure everyone can understand why that's important. And ideally, you know, you have flat sand-filled trenches. You don't want your cables, your hydraulic line to be kind of cattywampus going through the trench. You want it to be very neat and orderly with a little bit of slack so it can move. And also, I don't know if you noticed, but all of my hydraulics rising out of the ground were all insulated with just basic kind of Home Depot insulation. And that minimizes the flex of the hose a little bit. So that's really the last slide, but I think, okay. So I open it up to questions.
I may have missed this, but why exactly did you put in rigid inclusions on site 2? I think no,
That's a
no
great
specific.
question.
Okay, so someone recommended it and they just went for it, or okay, all right. Well, that's my okay.
That's a good question.
I had that conversation with before the presentation.
Thank you. Oh, sorry. All right. Thank you, Zach. Just a quick question. Did you have options on the second project to use manual settlement plates to shoot them?
As in optical.
Yeah, optical. Did you have that option too, in addition?
We tried to deploy an automated total station, but the contractor ended up bringing manual surveyors in
Okay.
because of cost.
Did you do manual settlement place?
Manual,
I believe that the contractor did
did you?
on site number 1.
Have you explored any more vibrating wire settlement systems? Because we've used that borehole settlement systems. Have you explored the using additional vibrating wire borehole settlement systems at all, or as opposed to one you're utilizing currently? Have you tried those at all?
I mean, I think it depends on the application, but we have, there's different types.
Oh, absolutely. But did you think of them on this project at all, or did you felt comfortable with the ones you used?
The site number one
Or
was
I guess number two.
straight out of the specification.
Oh, for sure.
I don't have a laundry list of different vibrating wire settlement systems in my mind right now, but I know there's various types. I mean, for example, we use a hydrostatic level system, which has a reservoir and then multiple nodes
Absolutely.
for like structural monitoring of, say, a grain silo or a storage tank. And there's other types with different ranges and different resolutions. So it just kind of depends on what's your expected level of movement and what's the installation technique that is going to keep it from being damaged during construction, I think.
Absolutely. I kind of keyed on that because I saw your piezometers. So again, usually when we had the drill rig out, we'd punch piezos and then punch those next to it. So that's why
Sure.
I thought about that. Absolutely. Well, thank you.
Yeah.
Yeah, I have two questions. The first one is more of a recommendation, just because I just got done redoing my kitchen water line to my fridge, but the 1/4-inch copper tubing that you use to run the water line to your fridge, could that be used instead of this plastic that has a higher rate of thermal expansion contraction?
Well, it isn't the PVC that's moving. It's the hydraulic line itself that's manufactured by Geocon. Does that make sense? So
Well, the hydraulic line being, is that a plastic material? or
yes, yes,
yes.
it is.
So a 1/4-inch copper piping might expand and contract less than what you're experiencing.
It would, I mean, I think practically speaking, Geocon has to roll these things up into a big roll. Sometimes your trench is 200 feet long for large scale embankments. So I think that I concede, yes, the thermal issue would be worse, but we have to weigh the practical installation aspect of, is it easier to unroll something? Or is it easier to be down in a water-filled trench, lowering down conduit? And then we would have to custom make all the connections.
Sure.
So, I mean, I should be clear, we bought all of this from Geocon, and then we put our logging system on top of it.
Sure.
So, but I agree, the material probably could be improved for less of a thermal effect.
Yep.
I think so.
So that's my suggestion. My actual question is the compaction effort. How was that applied? Is it a smooth drum roller vibratory? And did that show up in any of the data from these sensors?
Well, the first site, the LTP, we could probably just go back on the data, but I think we did see some initial pressure spikes. I don't remember the exact magnitudes, but when one of the things, actually, I'm really glad you asked this question. One of the protective measures that are really important, obviously you've got this earth pressure cell, it's a 9-inch diameter and it's on top of a steel load transfer plate. So obviously if you run compactor over it, you're going to overrange and break the sensor. So we actually had to compact sand and then put a burlap sack over it. And then we hand put fill up about another foot and at first we were just stomping, then we pulled out a hand compactor, and then they eventually came, I don't know what type of roller they used, but we had, I think, at least 1.5 feet or so of protective material and a way to contain that material before we brought in the heavy compaction equipment to protect the cell.
That could be a reason why some of that that load is not being seen. Perhaps that cushion that you've created to protect your sensor
Yeah,
may not have transferred as much load.
yeah, and that's a soil disturbance issue all over again.
Yep.
So there was a minor soil disturbance issue potentially at site 2, or no, at site 1, but it was far less than having an aggregate pier and uncompacted fill on top. I think we could both agree on that for sure.
Thank you.
Yep. I got a target on my chest.
No, I'm just on site 2,
Yeah,
looking at the bedding, you had a picture of silica sand. You were bedding the EPC instruments in silica sand. Any thought to perhaps you had a relatively open void in your stone column that with the rains, we washed our bedding away and
yeah, bedding issues. Yep.
I mean,
Yeah.
that's obviously a common concern, right? How you bed the instrument.
Yep. I mean, ideally, I mean, a layer of fabric prevents that. If you put fabric cell over. So, but yeah, I mean, it could have affected the readings. Yep. Great point.
Anybody else got any questions? All right, well, thanks to Zach. Make sure to say thanks to Zach again, because Zach bought your bar tab. Everybody at home, you're on your own for bar tabs. Reminder for everybody that next month we don't have this meeting, we have the actual Minnesota Geotech Conference. So look on the website, get registered for that. And then we'll see you all back somewhere. Yep, and we'll see everybody for the March meeting. Thanks, everyone.
Went all right.